Welcome back to the lectures in chemistry and the structure of atomic and the topic of atomic structure and chemical bonding. Okay. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras. Okay. My email addresses are given here for reference and for contact. The lecture now will continue from the last one on the variational method, but I shall discuss a little bit on the variational principle or variational minimization of the energy using the method of Lagrange multipliers in between the lecture. Okay. Now, recall that we were trying to solve the Schrodinger equation H psi is equal to E psi when we do not know all the eigenfunctions, even some. Therefore, we could use an arbitrary basis function set phi I such that the basis functions are preferably orthogonal, and this is an orthonormal set. And if the basis functions are not orthogonal, then we use the overlap between them, call it as Sij not equal to 0. This is delta Jk means j is equal to k, j not equal to k, this is 0, 0 j not equal to k and 1 j equal to k. Okay. If the functions are not orthogonal, we can define an overlap matrix with normalization as a possibility, so that Si we can always set it to 1 by redefining the wave functions. So, this was mentioned in the last lecture, but let us see it in the from the variational theorem using what is known as the method of Lagrange multipliers. Okay. Now, if we write the wave function in terms of linear coefficients Ci, phi I, if you want to write this, you can always write this as a ket, and we want to obtain the Ci's such that, get Ci's such that the energy is a minimum, the average value for the energy. The average value for the energy in this state is, if you write the integral formula, it will be psi h psi, and using the expansion of the wave function in terms of all the basis sets I equal to 1 to n. If you do that, you get the sum I j phi I h phi j, you get C I star and C j, because this is of course C I star phi I, this is C j phi j, and the Hamiltonian is sandwiched between the two. And you write this usually as the Hamiltonian matrix element H I j, and therefore, this expression for the energy is given as I j, both going from 1 to n. You have H I j, C I star C j. First, let us make some simple assumptions which are generally valid for the problems we deal with, that we will have real coefficients, and we will also have H I j, all elements of the Hamiltonian real. Okay. Therefore, H I j, due to the hermiticity property, it will be H j I. Okay. And the condition for the wave function psi to be normalized is the sum over I equal to 1 to n, the absolute values of Ci square. Of course, we are now using real values. Therefore, Ci square is equal to 1. Okay. This is the constraint in the choice of the Ci's. Okay, here. Now, if you look at it carefully, there are n coefficients which are not determined and which we want to know. Therefore, if we think that all the n coefficients are independent of each other and we want to minimize the energy as a function of these n coefficients, we have to remember that all these coefficients are connected by this relation that the sum of squares of these coefficients is equal to 1. Therefore, the expansion psi is equal to I 1 to n C I phi I does not have n independent coefficients, but has only n minus 1 of them because of the constraint. This is called the constraint, that the sum of squares of the coefficient is equal to 1. For a minimization of such problems of the energy as a function of the C1, C2, the Cn, what you want to do is to write dou E, dou Ci is equal to 0. Therefore, to do this with the constraint that Ci square is equal to 1, the method of Lagrange multiplier defines what is known as an L function, Lagrange function L, which is the energy itself psi h psi, but which includes the constraints, namely that E times psi psi minus 1. Okay. Therefore, what you have is the matrix, the Hamiltonian with the E multiplied by the constraint that psi psi is equal to 1. Therefore, technically this is 0, but remember now if we write this in terms of coefficients, you will see that this is I j C I C j h I j minus E times sum over I C I squared minus 1. This is called the L function, and the minimization for the energy is done by taking the dou L by dou Ci to 0 for all Ci I is equal to 1, 2, 3 up to n. This is called the method of Lagrange multipliers. Lagrange multipliers. Therefore, let us do the following. If L is as we have, you can just go back to the previous page. L is given by this. Therefore, if you take the derivative of L with respect to Ci, you will see that there is a Cj Hij, but it will be twice, and this is 2 Cie. Therefore, what you would get is when you take the derivative of this expression, you will get this form j Cj Hij minus Eci, that should be 0. This is dou L by dou Ci. And this is valid for I is equal to 1, 2, 3, 4. So, you have essentially the kind of expressions, namely sum over j Cj H1j minus Ec1 is equal to 0. This is for I equal to 1, and for I equal to 2 you have Cj H2j minus Ec2 is equal to 0, and likewise you will have n equations, namely j Cj Hnj minus Ecn is equal to 0. Now, if you look at this equation carefully, see, this is the same thing as the matrix eigenvalue equation we wrote down in the previous lecture on variational method, because what you have is essentially C1 H11 minus E plus C2 H12 plus C3 H13 plus C4 H14 and so on. This is 0. Okay? Therefore, it is easy to write this down as C1, this one, H11 minus E, H12, H13, H1n, H21 or H12 because they are both equal, H22 minus E, H23, H24 all the way up to H2n. You can see that this multiplied by C1, C2, C3 up to Cn is equal to 0. You can write this down, okay? All the equations. This is exactly what we had earlier. Therefore, the method of Lagrange multipliers is, it gives you identical results within this limitation of real basis functions and real coefficients and the Hamiltonian matrix elements being real, but this can be extended to complex quantities. I do not think it is a problem. The Hamiltonian is a Hermitian matrix. You only have to make sure that you take the right derivatives. But what is important is that this has already been identified, and the method of the multipliers gives you the same, namely the determinant of this should be 0, and therefore you will have n eigenvalues, and the lowest of the eigenvalues for various values of C there is what is called the variationally minimized energy. The only change is that if the basis functions are chosen, as you see here, we chose the basis functions as orthonormal, isn't it? Somewhere I have written that down. Let me see where I have it. Okay. The basis functions phi I, ij were assumed to be delta ij, and if you did not have that condition, then the energy expression that you have, the average value for the energy here, the average value for the energy will also contain an Sij, sorry, this is Hij, the eigenvalue expression E will contain here, this one. This will also contain an Sij because the coefficients and a corresponding Cj. Therefore, it will not be limited to one C's, but it will be, there will be many. What is the form of that equation? If the eigenfunctions, the basis functions are not orthogonal, but they have an overlap between them, then the Hamiltonian that we have to write will be H11 minus E. S11 would be 1, but then you will have H12 minus E S12, H13 minus E S13, all the way up to H11 minus E S1n, and likewise you will have H12 minus E S12, because the overlaps are also symmetric, H22 minus E S22, H23 minus E S23, and so on, H2n minus E S2n. All of this multiplied by C1, C2, C3 up to Cn, that would be 0. This goes all the way down to the nth element. Okay. So, either we use this if we are able to choose the basis functions to be orthogonal, but if the basis functions are not orthogonal and we have some numerical reasons for choosing them, that it is possible to calculate all these quantities H12, H13, all these things much more efficiently using functions which are not numerically which are not orthogonal. Okay. If that is the case, then you have to actually calculate the overlap integrals between the basis functions, and you ensure that the Hamiltonian that is diagonalized is this Hamiltonian. What you see here is this Hamiltonian equation, okay? The whole of it. The choice of Gaussian functions in the numerical calculations of the entire quantum chemical, the quantum chemistry, the entire quantum chemistry, the use of Gaussian functions is precisely for this reason, that they may not have a zero overlap, that is, they may not be orthogonal. It is possible to bring some orthogonal functions into them, but if they are not orthogonal, it is still possible for us to use them by ensuring that we calculate the overlaps appropriately and then numerically diagonalize the whole process. Now, for real problems, the n has to be a finite number, because computers cannot take n to be infinite. Therefore, the choice of basis functions is very, very carefully made, and the n, which is the total number of basis functions that one has to choose, is also controlled so that you have numerical efficiency in using computer time, in using the computer memory, and in getting the right result which is close to what you think should be the experimental result, how closely you can align yourself with the experimental results. All these things are important factors, but the variational principle is fundamental to all of that. Okay. Now, just two simple examples of this process, and one example is already something that you have done. The harmonic oscillator example you have already done in the last class or the last lecture. Please recall that we chose an arbitrary function for the wave function psi to be an exponential minus lambda x square, and we found out that for the Hamiltonian minus h bar square by 2m d square by dx square plus half kx square, we found out that lambda turned out to be square root of 1 by 2 square root of km by h bar square. Okay. And this 1 by 2, which is usually written as alpha, and therefore you see psi is e to the minus alpha x square by 2. We have done this, we have verified this for the variation method. Today we shall also look at, this time we shall also look at one more simple problem, namely a particle in a box. If we have the wave function psi of x, which merely satisfies the boundary conditions that it is a constant times x times L minus x, so that the wave function is 0 at both the boundaries, but otherwise it is an arbitrary wave function. What will be the average value for the energy using this wave function? Variational theorem tells you that this will be greater than or equal to E1. But in this case, of course, it is quite clear that this is not the eigenfunction. Therefore, we will see that this is actually greater than the E1, which the exact solution for the particle in the box gives you as h square by 8m L square. L is the box length. Let us see that very quickly. The average value for E is to be obtained with c square, the integral x into L minus x minus h bar square by 2m d square by dx square times x into L minus x dx. But since the wave function is not normalized and we have the c square, we should have it as the integral c square times the integral x square into L minus x whole square. It is c square times the integral x square into L minus x square 0 to L dx. Okay. Now, this is such an elementary calculation, you have done it several times. Therefore, let me write down the final answer for this. The energy, the C is given as root 30 by L raised to 5. You have already calculated this in some of the examples. The E is calculated as 5 h square, the average value, 5 h square by 4 pi square m L square. So, if you have to write this as h square by m L square, whatever the number you get here should be greater than 1 by 8. 1 by 8 is 0.125. If you calculate this number 5 by 4 pi square, you get approximately 0.127. Therefore, you see that the average value E is greater than the exact eigenvalue E1, which is h square by 8 m L square. Okay. So, this is a simple example of a variational method. When you have an arbitrary wave function, what you do is you calculate the energy. Of course, here we did not have any parameter. Therefore, there was no requirement for the parameter to be minimized. Whatever we got was essentially the average value as defined in quantum mechanics. So, it does not seem to be like anything to do variation, what kind of variation we did or what we varied, it does not seem to be coming out. But in the case of harmonic oscillator, of course, you saw that lambda itself was the parameter, and therefore, we minimized the energy calculation as a function. The derivative of that energy with respect to lambda was set to 0, and then we tried to obtain the minimum and predict that that is the energy that we should get from variational theorem. Okay. There are quite a few examples. What I would do is in an assignment or in a handout, I shall give you a few more problems directly using the variational method. But let me give you one slightly more complicated example. Suppose the wave function for the particle in a one dimensional box is given by two constants C1 whose function is x into L minus x, and another one C2 whose function is x square into L minus x square whole square. C1 and C2 are arbitrary constants, and the functions x into L minus x and x square into L minus x whole square both satisfy the particle in a box boundary condition, namely psi of 0 is 0, psi of L is 0. But remember, these two functions are not orthogonal to each other, because if you take the orthogonality property, you call this as phi 1 and you call this as phi 2, phi 1 star phi 2 d tau dx 0 to L, phi 1 phi 2 dx, that is not 0, it is 0 to L x cube into L minus x whole cube dx. Therefore, these wave functions are not orthogonal. Now, if we calculate the energy of the particle in a box as a function of this psi, you will get the following, namely C1 square, the integral x into L minus x times the Hamiltonian operator times x into L minus x dx divided by, we will do the division later, sorry, x into L minus x plus C2 square, this is 0 to L, x square into L minus x whole square, h x square into L minus x whole square dx, this is the second term, this is C2 square, and then you have C1 C2 plus C1 C2, the integral 0 to L x into L minus x, h acting on x square into L minus x whole square dx plus C1 C2, the integral 0 to L x square into L minus x whole square with the Hamiltonian acting on x into L minus x dx. Now you see that the energy that you obtain is a function of the coefficients C1 and C2. So, the variational principle here is that if we want this energy to be minimum, then we calculate dou E by dou C1 to be 0. We set this equal to 0 and find out the value by also having simultaneously the second equation dou E by dou C2 is equal to 0, because the energy is a function of two parameters and you have two conditions. You will get a value for C1 and C2 by solving this equation. Those C1 and C2, if you substitute in the expression for the energy above in all these 4, 1, 2, 3 and 4 terms, then you get what is called the variationally minimized energy. This is a trivial example for which we already know the solutions exactly, but the point is the exercise of how you should do for functions and for systems for which if we do not know the exact eigenvalue, the procedure is identical. That is why this matrix formulation was done a little earlier. When we do not know the correct eigenfunction, we only make a proposal and we have a lot of coefficients and we try to minimize these coefficients. Either the minimization or the matrix diagonalization, they both will give you identical results. From there, we can get to the energy eigenvalue. So, there are many other examples and you will see more and more when you move on to the next course in quantum chemistry and you want to compute numerically the properties and also start using numerical routines. You will see more of this. I have not given any mathematical concept here, but probably in the lecture notes that I might provide in this course, I will do a little bit of formal mathematical work. There are two beautiful books for those of you who are interested in looking at the variational method in detail. Okay? Let me write down those books, 2 books for you. Okay? The first one is Calculus of Variations, and the author is Robert Weinstock. It's a Dover Publications book, 1974. The second book is a little more into the mathematics of it. It's called Variational Principles in Dynamics and Quantum Theory. It's also an advanced book, and the author is Wolfgang Grau, G-E-R-E-U, and Stanley Mandelstrom, a well-known physicist. This is also a Dover book, 1979. They are both quite advanced, but variational method is an extremely important method. I will say much more of this in an advanced course, but in the introductory course, I think it is important to hear some elementary principles. But for those of you who want to follow this in more detail, these 2 books will provide you some of the best state-of-the-art variational methods used in quantum theory. Okay. We'll continue this with the first lecture in the next lecture on the chemical bonding, and we'll start with the hydrogen molecule ion as the first example. Until then, thank you very much.